Hey, thoughts before starting the material. There is a fifth problem set. It is actually due the next class, Wednesday at 1 o'clock. It's short, sort of acknowledging that there was a short time between last problem set and this one. So I don't want it to be an unwelcome surprise. Some of you were rather surprised by last week's problem set. So do it. Any other questions relating to the course structure stuff? I will remind you that the second midterm is coming down the pipe. I think it's the 28th of this month. So it's 2 weeks from today. All right. Well, where are things left off last time? I'm talking about balloons. And so my goal in this topic is to give you an idea why some balloons float, why other ones don't. But there are lots of things that come up as we look into why helium balloons, why hot air balloons manage to float up in the air that are relevant to your lives. And I will, thinking of them before class, I'll try to bring them in as they show up. And do ask me questions, because I've got a couple questions sitting here that prompt me to think of some of the other things that you ought to know about in the world around you associated with how balloons float. So, okay, to wind back, to remind you where things stand with balloons, in part it's the story of how fluids work. And fluids is a catch-all for things that can change shape. So it includes gases and liquids, and which word I use will vary as it just comes out of my mouth. So the world of fluids, they still have all those characteristics we've seen before, like mass, and things accelerate, and they respond to being pushed by way of accelerating and so on. But they need some new concepts in language, because they don't have fixed shape. They don't push on things quite the same way as, say, a block of wood pushes on the wall. And so concepts like pressure and density showed up necessarily. It's hard to talk about how gases work without talking about pressures and densities. And I'll remind you what those are. Pressure is how hard a fluid pushes on something per unit of surface area. So it's like force, except it's force per surface area, and takes into account the fact that fluids sort of have often poorly defined sizes and so on. And so how much force the air is exerting on the wall over there has both to do with the air and how big the wall is, how much surface area. And just as a useful things to know, the metric unit of ordinary atmospheric pressure, the metric amount, some of you may find useful and some of you may not, but it's 100,000 newtons per square meter, or 100,000 pascals. It is, it just is that value, approximately. It's more like 105. It actually varies with the weather, which is an issue I'll try to bring up. And for those of you who are more comfortable with pounds and square inches and stuff, it's a little under 15 pounds per square inch. So the air is pushing on the top of this syringe. Yeah, you ready for your flu shot? That's about a square inch up there. It's exerting about almost 15 pounds of force on that surface. Okay? So that's pressure. We will see that things respond to pressure just the same way they respond to force. They tend to accelerate. And we'll see, in fact, that pressure differences cause things to accelerate, even the air itself. So if you have high pressure here, low pressure there, there's an imbalance in pressure. The push to the right is stronger than the push to the left. The whole chunk of air will accelerate toward the right. All right, so that's pressure. Density. Density shows up because it's interesting to know sort of how much mass does the air have. So density is related to mass. And since air doesn't have necessarily a well-defined size, you want to characterize the air kind of independent of how much you're talking about. What's the air like, whether I have a little or a lot? Well, it has a certain amount of mass per unit of volume. And the SI metric unit of volume is the cubic meter. So about a cubic meter of air has a mass of about 1¼ kilograms. I mean, You may never remember that. I remember it because sometimes I find it useful. So it's somewhere stuffed in there. And the imperial unit, yeah, I know, like per gallon. I don't know what the pressure of air is per gallon. I could figure it out, but it's density. But anyway, it's mass per volume. Okay, that's density. And things have densities other than fluids. They're densities of solids too. It's just mass per volume turns out to be a useful measure from time to time. All right, so the reason gases have pressure is thermal energy. The gases are assemblies of little individual particles, that is atoms and molecules bouncing around with thermal energy. In the absence of thermal energy, they would not be a gas. It would just collapse into a lump. So the independence of the particles depends on thermal energy. And that's why when I took enough thermal energy out of air inside a balloon, it stopped being gas. It condensed into in fact, a liquid. We had liquid air inside the balloon, and you can just put a lot of molecules in there in the liquid form. And then when they warm up, they turn back into a gas, and we blew up a balloon last Friday that way, by overfilling it with liquid air and then having it go to gaseous air. All right. A thought that's going through my mind is that liquid air used to be a very useful material in maybe about the 1900. They would use liquid air as a refrigerant. You can liquefy it by running a very powerful refrigerator. You turn it, cause the molecules to stick together and collect. And so liquid air was used as a coolant for various things. There's a problem with liquid air sitting around. So this is sort of tools for a living. You notice I was playing not with liquid air up here, and I can play with it again, but rather liquid nitrogen. I think has Al brought it back yet? Yeah. So I'll use it again. Liquid nitrogen is created in a powerful refrigerator using a technique that we'll talk about later in the semester. And the molecules have so little thermal energy that they stick to each other and cling and form a liquid. So that's liquid nitrogen. Now, I can make liquid air by just using liquid nitrogen to chill air. And we'll end up with liquid air. The problem with liquid air is this. It contains oxygen and nitrogen and a couple of other things that are in very small quantities, primarily those two. And you know from grade school and beyond that the air around us is about 80% nitrogen, 20% oxygen, right? This is sort of old factoids you might remember. Well, nitrogen boils more easily than oxygen does. So if you have a container of liquid air sitting there like that, the nitrogen will come off first, leaving behind oxygen. So liquid air left in a container like this for a week, what's left at the end when the last little bit is still boiling away is mostly liquid oxygen, which supports combustion very nicely. So there were some tremendous fires, say in the early 1900s, because people used liquid air and let it sit around too long. Solution, get rid of the oxygen from the start. So generally the machines that create liquid nitrogen now distill away the oxygen. They may well use it for something useful, but they know that's the stuff that supports combustion. Be careful with it. So this doesn't. All right, to get back to the world of gases again. So that's nice and cold. One thing I showed you is that the pressure in a gas, because it comes about because of thermal energy in the gas particles jiggling around. If you slow them down by cooling them, the pressure, and do nothing else, the pressure goes down. The particles are moving less fast. They hit less often. They hit more gently, whatever they're hitting, so there's less pressure. They just don't push on the... If we chilled all the air in this room down by a factor of 4, which is, I'll come back to again, and did nothing else, the particles would be hitting the walls less often, because they're not traveling as fast, and when they hit, they would hit less hard. The pressure that they have on the wall would go down by about a factor of 4. They go together, pressure and temperature. If you don't change anything else, they track beautifully together. So you can lower the pressure by lowering the temperature. What temperature am I talking about? It turns out you got to be careful what you choose as the temperature scale. You have to use a temperature scale. When I say reduce it by a factor of 4, that means get 4 times as close to the real zero of temperature. And the only real zero there is not the 0 of Celsius or 0 of Fahrenheit. It's absolute zero. It's the zero, it's where there's no thermal energy left. And you can sort of imagine that can exist because you just get rid of all this random motion that you can't pin down. The motion, when I do this, I'm getting the molecules and particles going faster and jiggling more. Do the opposite, get them to just sit there. And as an aside, there are people in this building who experiment with systems that are within probably a billionth of a degree or of a standard unit of temperature from absolute zero. They don't go quite to absolute zero because you can't get there. It's just too hard. It's like winning the lottery a billion times in a row. How are you going to find the last little bit of thermal energy to remove it? You can't do it. But you can get really close. And so using techniques that involve lasers, actually, you can cool atoms down to the point where they're just about at absolute zero, but not quite. And interesting things happen there. Oddly enough, you can keep a gas of these particles around at that very, very low temperature. The particles are moving at sort of walking speed. They're so slow. If you went all the way to zero, if you could do that, they could no longer be a gas. But they're just the last inch away from being at absolute zero, and so they are a gas. And then people play with them, do experiments. So one of the questions that came in is what actually happens at absolute zero, and you just can't get there. Everything is a solid at absolute zero with 2 exceptions. Helium remains a liquid at absolute zero, oddly enough. And that has to do with quantum physics, not with classical physics. And in principle, hydrogen atoms remains a gas at absolute zero, but again, it's quantum physics. So basically, everything just sits there and has no mobility. All right? So just to come back to balloons. Lowering the temperature of a gas by, say, a factor of 4, in approaching absolute zero by a factor of 4, you lower the pressure by about a factor of 4. That assumes that you don't accidentally create a liquid, which okay. How else can you change the pressure of gas? Change its density. Why density? Because density measures mass per volume, but if you reduce the density of air, say, by a factor of 4, that means you have only 1/4 as many air particles in the container. So they're just fewer of them. And they hit less often because there are fewer of them. They still have the same thermal energy. We didn't change their temperature. So we simply changed their abundance. And if you cut them out by a factor of 4, you lose about a factor of 4 in pressure. The point of all this harangue is the pressure in a gas depends primarily on its density and its temperature. And it's almost related to a product of those two. You multiply its density times its temperature, and within a constant, you end up with its pressure. So you can change the temperature, increase the temperature, the pressure goes up. Increase the density, the pressure goes up. Increase them both, the pressure goes up a lot, and so on. What this is a piece of the ideal gas laws, the laws governing gases. The word ideal shows up because it assumes simplicity that's not entirely true. Like nitrogen or air or oxygen, those systems, if you muck around with the temperature, the pressure goes with. You got to be a little careful though. If you take the temperature too low, the whole thing falls apart because you create a liquid. That's non-ideal behavior. That's the problems that the ideal gas law doesn't want to consider. All right, so pressure, density, temperature. Any questions about pressure, density, temperature stuff in gases? Can you go below absolute zero? No, it's a real zero. It is as far down as you can go. There was an old Superman episode from the 40s in which they freeze Superman at 2,000 degrees below zero. Sorry, can't be done. Of course, Superman. Yeah, all right. Other questions? All right. Well, that got me to the next thing, which was the air pressure around here. I told you it's here. The air pressure is about 15 pounds per square inch, 100,000 pascals. Where does it come from? It comes about because of gravity. If there were no gravity, the air would just spread out as far apart as possible. The pressure would drop to zero. That would be that. Our air particles would drift off into space. So they're held in place by the Earth's gravity. Fortunately, the Earth's gravity is strong enough to keep them in place. Smaller planets lose their atmospheres. Gravity is not strong enough. The particles are traveling fast enough that they actually can sort of sail off occasionally into space and never return. I should tell you how fast the particles are traveling. Because if you remember, rockets, we talked about in rockets that sort of getting up into the orbit and so on, you wanted to go about 15,000 miles per hour, 20,000 miles per hour. Well, air particles aren't traveling that fast, but they're traveling really fast. So the average guys in my hand right now are actually moving at about 300 or 400 meters per second. They're traveling a good fraction of a kilometer per second, which is pretty fast. And you might think, well, okay, if they're going that fast, why don't I notice it? Because they don't make much progress before they hit something. So they're just bouncing around like crazy, bouncing off of each other. And as a result, they don't make extensive progress, any individual one. They're mostly sort of sit around and jiggle in place vigorously. They do actually statistically make some progress, though, and you know this because if somebody opens a bottle of perfume, say up here, you'll all start to smell it after a while, right? It'll drift. Even though there's no air currents, it will gradually diffuse, it's called, through the room, and that's the random motion of the particles. They finally make a little more progress, and actually you can learn about the molecules in the perfume by how long it takes them to make progress. The bigger they are, the slower the progress is. All right? So, the particles do travel very fast. The ones that travel the fastest are the ones with the lowest mass. And those are helium and hydrogen. Hydrogen, actually, I should point out, hydrogen doesn't exist in normal situations as an atom. It's essentially always found paired with another hydrogen as a hydrogen molecule, H2. They stick like crazy to each other. And so when you compare helium and hydrogen, they are very light. But if you looked at the periodic table and so on, you might think that the hydrogen atom has a mass about 1/4 of a helium atom, which is true. But hydrogen, as you find it in nature, is only half the mass of helium because it's a hydrogen 2. Helium, on the other hand, is a very aloof atom. It doesn't care to stick to anything. In fact, it barely sticks to itself. As a consequence, helium basically remains a liquid even down to absolute zero. What else? Okay, so those guys travel very fast. And as a part of the story about how gases work and why helium balloons float is because even though a helium atom is so dinky, has such little mass, it does its share of creating pressure. The same as a nitrogen or oxygen molecule. The particles in any gas, so in my hand right now, there are certainly nitrogen molecules, that's N2. 2 nitrogen atoms glom together. Again, they stick like crazy. You'll never find a nitrogen by itself. I mean, there are probably a few of them in this room, but like a countable number. Same with oxygen. It hates being by itself. They pair up. So in my hand, there are nitrogen 2s, oxygen 2s. There's some neons. Neons don't pair up. They're happy to be aloof. The various other noble gases, xenon, krypton. There's a lot of water, which is a topic we'll come to down the road. When you see the analysis of the Earth's atmosphere, there's a little asterisk saying, in dry air, that's air without the water. They're actually about 2% of the particles in my hand right now are actually water molecules, okay? And all these particles are contributing to pressure. they're buzzing around and hitting stuff and creating pressure. And the little dinky heliums, I should say, there are some heliums in there, not many. It's an important issue that helium is a very rare material on Earth. It is not present in the atmosphere to any reasonable amount because the helium atoms in my hand are traveling so fast in order to do their job of creating pressure. They carry their thermal energy. They're traveling so fast that if they manage to get to the top of the atmosphere, they can leave. They head off into space and we never see them again. So whereas most of the atoms in our atmosphere, or molecules in our atmosphere, essentially never escape. Nitrogens and oxygens, sorry, gravity keeps them here. Helium and hydrogen are the two exceptions. They travel so fast with their little thermal energy that they can escape. And so most of the helium on Earth leaves when it gets to the atmosphere. So why do we even have any helium around? We have helium around because of radioactive decay deep in the Earth. And it shows up in natural gas. So all the helium you all have played with your whole lives, all the balloons, the tank over there, that comes from natural gas wells, where radioactive decay created these little helium nuclei. They come from what are known as alpha particles. It's not, beyond nothing we need to worry about. They come along with natural gas, having accumulated there over millions, billions of years, and we play with them and then we release them into the atmosphere and they escape. And so probably within your lifetime, helium is going to become a precious resource where people become quite concerned about running out. And it's more than just fun and games for kiddie balloon parties. Helium's kind of important, and it's going to be a problem, more for you than for me, but it's just so you know. So helium escapes. All the particles then do their duty to create the pressure, and they're down here held in place by gravity. And because of what gravity does, gravity's pulling on all the Earth's atmosphere, pulling it inward. Well, you think the air down here has to keep the air up there. It has to push. So the air down here has a lot of pressure developed in order to support the air above it. If no pressure ever developed as gravity pulled in on these particles, they would all come down. They would assemble down here and be a big slurry on the floor. But instead, the thermal energy allows them to lift up and push up. The ones down here are pushing the ones up there. And when the whole situation reaches equilibrium, you discover that the air down here has a density of about 1.25 kilograms per cubic meter in order to develop enough pressure at ordinary temperatures to support the air up here and everything up above it. Because I suppose there's the old Dr. Seuss book, Yertle the Turtle. You guys still read this thing? With all the turtles stack up on top of each other to try to let what is it, Yertle who's the top one, or is Yertle the good guy? I forget. Anyway, the king wants to be on top or something. Typical. So the lowest turtle's supporting all the weight of all the turtles above, right? The top turtle supports nothing. Life is easy until they fall off in the mud. Same with all the air here. The air is piled up, big stack of air going way up. And in order to support all the air up there, the air down here has to develop a pressure of about 100,000 pascals. Where did that number come from? It comes from the weight of all the air overhead above a square meter of surface. You need to push up with about 100,000 newtons. So the air pressure down here supports that stack of air. The higher you go, though, if you go and take a tall elevator up, you'll find that the air has lower pressure as you go higher because it's not supporting as much weight. And in order to have less pressure, it needs one of two things or both. It needs a lower density or a lower temperature or both, right? I already talked about pressure and temperature and density, the relationship. And that's what happens. So when you go up in the Blue Ridge to greater altitude and therefore higher up in this stack of air, the density goes down along with the pressure. The pressure goes down, and with it, the density goes down and the temperature goes down. They're both temperature and density are at work lowering the pressure. Is that okay? So, which takes me to one of the questions. What happens when air doesn't have water in it? It's fine, and you can make dry air if you interact with it as a person or as a creature. You will statistically lose water molecules to that dry air, and they will not come back very often because they're lost. And so you find it very drying, and this is what happens, for example, when you go into an airplane. The air there's almost free of water molecules way up high, and you dry out. Otherwise, not so important. But one of the questions that came in here is can density change, say if temperature changes? Is that the one I wanted? Yeah. Can density change if temperature changes? And you all are now witnessing outside that the temperature is getting colder. And what does that cause? So the air outside is getting colder. Well, its pressure can't go down a lot. I mean, the first thing to think is, well, if temperature goes down, pressure goes down. But if the pressure goes down, then it's not pushing as hard on the stack of air above it. Ooh, that's a problem. The stack of air above it then begins to descend. And this is actually real. It begins to descend and pack the particles more tightly together down here. They're not being pushed up enough. So the density goes up. So as the temperature goes down outside, one of the first consequences is the density begins to increase down here in order to summon up more pressure to support the stuff overhead. But the whole column of air from the ground up to the top of the atmosphere, which is some number of miles, it's tens of miles, but not much more than that, that whole stack sort of sinks down and squishes down. And as a result, the air over on the side of that stack, so this is Charlottesville, cool down, everything sort of squashes in order to, there's not as much pressure pushing up initially, and so it squashes. And over here in some hot spot, I don't know, Crozet for some reason stays nice and warm, the air up at the top of the atmosphere goes, ooh, I can release some of my potential energy. Remember total potential energy? Things like to accelerate so as to reduce their total potential energy. The stack is still tall over there in warm Crozet, and therefore the top of the atmosphere sort of falls over. It flows over to fill in that low spot. Like water in a swimming pool, it's suddenly discovered there's a low end. So it flows over, and the stack down there in that hot part therefore has less weight over it. It expands, it undensifies, or what's the opposite of getting more dense? Less dense, obviously. So it gets less dense, and as that happens, with less weight overhead, the pressure drops. So you get low pressure down at the bottom in the hot area. Slightly lower, I should say. It's a little lower over the hot Crozet than it is over cold Charlottesville. And this causes the air in Charlottesville, which is higher pressure, to push the air in between here and Crozet towards Crozet. It accelerates. Where I'm going with this creates a cycle. You create the winds. Where do the winds come from? It's not a mystery. This is how the winds develop. You cool the air in Charlottesville. The air down here descends, stacks more tightly, and at high altitude, air flows toward Charlottesville, and at low altitude, air flows away from Charlottesville. So the ground winds blow towards the hottest place. The high altitude wind blows towards the coldest place. And it creates a cycle like this. And it's got to do with the changes in density and pressure that come with temperature. You okay with that? So this is why, for example, between a shore and water, so if you're in a bay or the ocean or something like that, the temperature over an ocean is pretty constant. The temperature over land tends to go up and down with the sun. And so when it gets hot, when the sun comes up and it gets hot, you tend to get air expanding and the pressure dropping in the vicinity of the hot shore, and air blows toward shore as the land heats up. And so in the morning, the winds tend to be onshore. And in the evening, when the land begins to cool off, which it does faster than the water. Then the land is the cold spot. The air comes toward it near the surface. So did you move backwards? It's the cold spot. The flow of air is always for the hot spot. It's offshore winds in the evening. So it's the origin of those winds. And particularly relevant during the summer and the early fall, the hurricanes, where do they come from? Well, if you get a good hot spot on the water, then you get air rushing toward the hot spot to rise up there. And that air rushing in toward the hot spot, if it's on a global scale, the airflow is very big, it encounters angular momentum issues associated with the rotation of the Earth. And that causes it to veer to the side. And so you get these circulations that occur, the famous, around the eye of the hurricane and so on. So it's a whole story, but I could go into it and I won't. All right, so the winds come about for these same reasons. But the key point for now is the structuring of the atmosphere, that basically it's high pressure, high density down here, also the temperature we're used to. And as you go up higher and higher, you lose, all three of them go down as the stack becomes shorter. All right? I think that'll do it. Okay, so that brings us then back again to balloons. Now we have a situation where the table's set so we can look at how a balloon floats. And here's the key observation is, the air down here is very busy supporting the weight of the air above it. And I can do that on the sort of the scale of the whole atmosphere, or whatever. But I also can tell that story on the scale of just this chunk of air in my hands right now. This chunk of air right there, and we're assuming no winds, to get rid of the wind. So that chunk of air, if I take my hands away, it hovers. It's not going up or down or left or right. It's just sitting there. It's inertial. So the net force on it is 0, right? And that air has weight because it's got a density, which means there's a certain amount of mass in my hands. And to do that, it's 1.25 kilograms per cubic meter times how many cubic meters are in my hand. I don't know, a little, teeny fraction we are. But it's got a mass, and therefore it's got a weight. Something's holding it up. And the something that's holding it up is the air pressure around this chunk of air. And if I had air paint, I could paint the whole thing. So picture it there. My head puffs up. All right, so there it is. I painted the air blue. There it is. It's being supported, despite the fact that it's got weight, it's being supported by the air pressures around it. Now, if the air pressure were totally uniform around it, and I've told you the air pressure around here is, 15 pounds per square inch? It's not uniform. It can't be uniform. If the air pressure were uniform there would be no overall push on the chunk of air I've got in my hand. So it would have only its weight acting on it, and down it would go. So the air pressure around this chunk of air is actually non-uniform, just barely non-uniform, but it is non-uniform. The air pressure at the bottom is a little higher than the air pressure at the top for the very reasons that I've been talking about. The air pressure down here is higher because it's supporting the whole stack of air to the top of the atmosphere, including the stack that's only this tall, right? The air up here this is like the bottom turtle, and this is the second turtle, right? It's a little higher. The pressure's a little lower there. And there are instruments that can measure this difference. It's a little hard for a human to do it, but it's true. So the air down here has a higher pressure. It's pushing up on this surface a little harder than the air pressure here is pushing down on the surface. And it's real. And that creates a net force on the portion of air. And we know what that net force is. It is exact. So I'm identifying a blob of air. But if I take the balloon away, the blob's still there. It's being supported perfectly. So the net force on that blob of air is exactly equal, is 0, it's being pushed up by the surrounding air with a force that's exactly equal to the weight of the blob of air. And that force is called the buoyant force, and we know what the buoyant force is. We know how much it is. The buoyant force on this blob of air, it's an upward force equal to the weight of that air. So far so good? I'm going to leave it at that for the moment. Another question coming in about tornadoes. How do tornadoes happen? Tornadoes are driven by winds, so you can set this aside for a second. They're driven by the winds. Again, it's the air, in effect, rising off the hot areas and coming in from the colder areas to replace it, these cycles. And it's, if there's a little bit of misalignment in which way the air is flowing, suppose it started like this, coming along, like, flow from one side, and they're not going to hit each other. They're going to miss the two flows of air towards this central rising pillar over a hot spot. If they miss, they carry angular momentum with them about that center. And as they come in closer, their overall rotational mass shrinks. Because remember rotational mass, that if I begin to, I can rotate slowly with my arms outstretched and have a fairly large amount of angular momentum. Why? Because my rotational mass is big. But if I pull in, my rotational mass shrinks. And in order to keep the angular momentum that I had, I got to go faster. So that's what's happening with a tornado. The air in the sort of overall area, the region, has some rotation to it, and therefore has some angular momentum with it. And as it works its way towards the center and effectively shrinks its rotational mass, it's got to spin faster to keep that angular momentum, and off it goes. Is that okay? I realize that some of these are taking us afield, but you ought to know these things. I mean, they're useful. I think they're useful. I hope you appreciate it. Okay, so back to this notion of this balloon being held up, this blob of air being held up by the air surrounding it. The air surrounding that balloon pushes up with a force that is upward and equal in amount to the weight of the balloon's air. If the balloon were bigger, so it has more weight, it would displace more of the surrounding air. The air would push up on it harder. Is that okay? So this leads to Archimedes' principle. And Archimedes' principle is the observation that we know exactly what the upward force is on an object immersed in the air here at the surface of the Earth. So, how much upward force does the air exert on this bottle? And it turns out it's exactly equal to the weight of the air the bottle is pushing out of the way, displacing. And I know that because if I visualize the bottle, and I'm going to take the bottle away, here's the air. It's a bottle-shaped chunk of air, and it's not doing anything. It's sitting at equilibrium. It's evidently supported perfectly by the surrounding air. So the surrounding air is exerting an upward force that's equal to the weight of a bottle-shaped blob of air. And the surrounding air doesn't care whether it's supporting air, its compatriot air, or whether it's supporting a bottle. It doesn't care. It pushes just as hard. So that's Archimedes' principle in open air. How about Archimedes' principle for water? All the fluids here near the surface of the Earth, air, water, pick any gas you like, pick any liquid you like, they all develop buoyant forces. And the buoyant forces are always, the buoyant force on an object immersed in any of those liquids is equal to the weight of the liquid the object displaces. So for example, this cylinder right now is displacing air, which gives it a teeny tiny upward buoyant force. But I'm going to allow it to displace not air, but water. And what will happen is the weight hanging on this stack of stuff, which is right now is 13 units. The weight will decrease because, here we go, I'm going to displace water. Here you go. Psh, water's there. The water is now pushing up. It's not touching. I have it so it's not touching anything in the container. Just the water. The water is pushing up on this cylinder with a force that's equal to the weight of the water displaced by the cylinder. And we went from 13 to 9. So that's 4 units of upward push from the water. So far, so good? And to show you that 4 unit, that cylinder size portion of water weighs 4 units, I can put that water in another cylinder, same size cylinder. Here goes the water back in. And this guy will read 13 because I've added 4 units of weight to the system. Right? Yay! Physics worked. So the water in the beaker is pushing up with 4 units of upward force, which is the same as the weight of a cylinder's worth of water. Okay? So the whole story then comes down with balloons. The whole story comes down with balloons is if you make a balloon that weighs less than the buoyant force on it, it will have a net upward force. So the balloon, this balloon has air inside. In fact, it's a little bit above atmospheric pressure, and I know that because the elastic skin of the balloon is pulling inward. And in order to have this, for this to be in equilibrium, the air inside has to push outward a little harder than the air outside pushing in to make up for the elastic character of the surface of the skin of the balloon. So this guy, the air inside there weighs a little more than the air it displaces, and it has a rubber skin that weighs something too. So this guy weighs more than the buoyant force on it. Not a lot more, but a little more. And as a result, the net force on it when I take my hand out of it is downward, and it begins to drift downward. It doesn't make much progress in a hurry because of air resistance, but it weighs too much. If we can lighten the load in that balloon, then we can get it to float. And there are 2 easy ways to do that. One is to go to hot air. If we take the air inside this balloon, we take it out, and it's got a certain weight. We put it on the scale, and it weighs 10 units. If we replace that air with hotter air at lower density, it can have the same pressure. So we're going to we'll take the air out, and we heat it up, and then we let it expand to twice the volume. But we have increased the temperature enough that even though its density is down, its pressure stays the same. Is that okay? The idea that you can do too many things at once. If you just heat it up and don't let it expand, its pressure doubles. And if you put it in here, it'll pop the balloon too big. So heat it up and then take half the molecules away. And now you're back to the same pressure. And put it back in here. So now you've got a balloon that weighs, the gas of which weighs half as much. And as a result, it might weigh less than the buoyant force upward on it. And so to do that, you don't want to go through everything. Where's the balloon? It's not here. Yeah, I brought everything out except the hot air balloon, so I don't have the hot air balloon. One sec. I can still talk. I can't see whether you're doing things that you shouldn't be doing. I'm back. All right. So this is a hair dryer for people with hair that's made of steel wool. Super hot hair dryer. And I'm now going to fill this balloon, not with room temperature air, but with air. Is it going to go? Come on. Aim. But with air that's hotter than room temperature. So what's inside the balloon right now is pretty much atmospheric pressure. We know that because if the pressure inside the balloon and the pressure outside the balloon were vastly different, things would move, right? So it's about atmospheric pressure, but its temperature's higher and its density is lower. So it doesn't weigh as much as it would if it were full of cold air. And up it goes. All right? the original versions of these things, these balloons are solar heated. And so you can get them going, and then they can float off into the way up high and cause trouble for air traffic. So you gotta watch out. All right, so clear how that one works? The other possibility is to use a gas that is itself very light, even when it's at room temperature and at ordinary pressure. For example, helium. So helium, let me get this out. And then I got one more demonstration to do after that. I can save some of the other things. So I'm putting in, instead of ordinary gas, ordinary air, I'm putting in helium atoms. Each helium atom does just the same job of creating pressure that a much more massive air molecule would put in. This assumes I let the air out of the start, which I might not have done. Anyhow, that balloon weighs especially, it's light. It's light because it has the same number of particles inside it that it would if it were full of air. And that's actually kind of a remarkable result, that if it had a zillion and 7 air molecules in it, if it were blown up like this, it now has instead a zillion and 7 helium atoms. And they weigh so little that the buoyant force in this should be well more than its weight. Yep, up it goes. All right, so hopefully you understand now why the helium goes up. Same number of particles. In fact, what's known as the particle density, how many particles there are per cubic meter, is the same whether you fill it with air or whether you fill it with helium. And that's a remarkable result. I'll leave it from the discussion, but it's remarkable that helium is just as good at making pressure as air is. And so it weighs much less overall than the air displaces, and up it goes. But it's not the only lighter than air gas. You're familiar with hydrogen, which we could use, and that would be, yeah, okay. The Hindenburg. The problem with the hydrogen is it's flammable. But there is another much more widely available lighter than air gas, and that is natural gas, specifically methane. I'm not talking about propane, sorry, propane's heavier than air. The particles are big. But the particles in natural gas are dinky. So I need a pyromaniac to light the methane bubbles. Somebody? Damien? Okay. You're the lighter, I'm the bubble blower. So we're going to make soap bubbles. Is this going? I hear it now. There you go. You get to light the bubbles. I'm going to blow the bubbles here. So we just got, okay. Don't light it until it begins to float up. Let me launch these guys. You can get close. You can go up there. Let's get better bubble sauce here. Okay, you can light. And even if I pop it, it will still float up. And if we did this with hydrogen and oxygen, it would work also, and it would be deafening. Hydrogen and oxygen bubbles explode. Okay, there you go. So even though that one popped, it was still there for Damien to light. Okay. All right. So my friend in high school used to make bags like that full of natural gas with a fuse on it, light them, send them up a couple of 100 feet where they would burst into flames, and then he would listen to the police radio for UFO reports. All right. So one more bubble, and then we'll see you on Wednesday. All right.